Thank you for the introduction, and as everyone else, it's an absolute great pleasure to be here. So my talk will be in a very similar spirit as Panayiotis' talk, where we try to really understand constant step size stochastic gradient descent for non-convex objectives. And but we're going to take a very different approach using continuous time approximation. And this is joint work with my second year PhD student. This is primarily, I would say, driven by Xiang, who is my second year PhD student, my postdoc Debang, and another PhD student Liang in my group. And I have to also admit that this is really a very new topic that we started to explore 2 years ago. And many of the results that I discussed today are really freshly baked. We've had the archived version released just last week. So very happy to hear. I know there are many experts here, so we're very happy to hear your feedback. Any suggestions, comments, or criticisms, if any. Yeah, cool. I know that we're a bit, strict with time, but I do want to spend 1 minute to give a special thanks to 2 people in the room. And the first is Radu for very inspiring discussions we had during my visit last time on using OD perspectives to analyze gradient-based methods. And this has really motivated us to look into more like dynamic system perspectives for studying stochastic algorithms. And then also to, I say, the great Panayiotis for also providing us a lot of useful reference books when my students started to, dive into this topic. And this is also evidence to show you that French do reply emails on a Saturday, you see there. Yeah, cool. So let's get to the business. As I said, the interest here is that we're going to look at stochastic gradient descent to solve stochastic optimization problems. And here particularly, we're going to assume the objective is smooth, but perhaps non-convex, right? This is the most popularly studied algorithm stochastic gradient descent here. Right, so there, of course, a lot of existing research has already established many non-asymptotic complex analysis for stochastic gradient descent under diminishing step size for how it will converge to a stationary point. Right, there are lots of really excellent work out there. However, I claim that there is really a very huge, I would say, very wide gap between the theory there we have established and also the practice. Right, in practice, oftentimes constant step size are more preferred than diminishing step size, and oftentimes gives much better performance, especially in like practical deep learning, for example. And with this non-diminishing noise, oftentimes we see that stochastic gradient descent manages to escape from inferior stationary points, such as like high loss local minimum, or say, for example, saddle point. And oftentimes they manage to select the good ones, right? These good ones could be the ones, say, for example, that are like flat minima. And these are oftentimes believed to yield better generalization properties for machine learning tasks, or gives you better robustness, especially if you have distribution shifts in your objectives. However, many of these phenomena does not really cannot really be fully explained by the current theory we have, because they do not really distinguish between different stationary points. So that means we really needed to build new analytical tools if we want to understand all these escaping behaviors or minimal selection behaviors of stochastic gradient descent. Okay, and stochastic differential equations has recently emerged to be a really promising tool to analyze stochastic gradient descent, right? As some of you pointed out that there are lots of already very well-established rich theory about regarding to the stationary distribution of stochastic differential equations, or SDEs, and this can be used to analyze, the long-term behaviors or limiting dynamics of stochastic gradient descent. Recently, there are also lots of attempts that tries to characterize or quantify what is the transitioning between different stationary points, particularly what are the interplays between escaping time versus the step size you choose, or the finiteness of the minimum. In particular, there is a very nice work by, I think, Mert and also co-authors on how to use Levy process to understand SGD under heavy tail noise. Of course, there are also some work that use stochastic differential equations to analyze also like the implicit regularization effects of stochastic gradient descent. And here is just to say, for example, one example, just to give you an illustration. Here we plotted 8 different rounds of stochastic gradient descent using the same constant step size with same initial points. Here's just one-dimensional example where you see in this example, there are actually 3 local minimum that with the same optimal value, right? It's like when x is equal to -1 or 0 or 1, these are all gives you the same optimal value. And for SGD here, we're going to initialize SGD all from these local maximum points here, okay, for all of them. And here is kind of the trajectory of stochastic gradient descent with 1,000 iterations. And as you can see that in most these rounds, actually, stochastic gradient descent manages to converge nearby to this flat minimum here, right? In this case, the red dot is the terminating points for all of those then. It is also interesting to see that if you look at this first plot, or the third plot, the fourth plot, or here the sixth plot, you see that initially stochastic gradient descent will actually get stuck in this other local minimum here, right? But eventually it will be able to manage the escape from it. So this is basically kind of the typical phenomena we observe with stochastic gradient descent, and that's something we want to understand. And I'll say that many of these existing SDE approaches follow a very common recipe here, right? First, we try to build some SDE model to approximately track the dynamics or the distributional evolution of stochastic gradient descent. And then we try to, based on analyzing the behaviors of stochastic differential equations, we then use it to predict or to interpret what's exactly going on with stochastic gradient descent, right? How do we measure what is approximation or what are the connections between SDE and SGD? So in numerical analysis, right, the standard notion of approximation is the so-called weak approximation, right? That says that if you're given all the test functions from a given class, right, from some class, and we wanted to the conditional expectation of your SGD dynamics and the SDE dynamics under any given arbitrary initialization is close to each other, right, within finite time. Particularly, we call it an order P weak approximation if this error is of order eta to the power of P. Okay, so this is kind of the well-known notion called weak approximation. Yes? In this context, we're going to look at all smooth functions up to some order, like say twice differentiable, third differentiable functions. At least a third differentiable actually in our context, but yeah. So intuitive, this basically means that we're really marrying this closeness with respect to distribution, right, rather than like individual sample paths here. So clearly, what you can see that how well you're able to approximate SGDs would determine like exactly how precisely you will reflect what is exactly the behaviors of SGD, right? That is basically the central question. Here is how well does SDE approximate SGD? Surprisingly, we shown that actually lots of the existing SDE models does not really do the job very well, and I will give you some examples. Before that, I will just maybe have a warm-up and start with the noisiness setting where everybody is more familiar with. So let's start with, so the simplest, of course, OD approximation for gradient descent is what everybody knows is the gradient flow. And if you do, say, for example, backward error analysis and including all the eta terms in the analysis, one can come up with this so-called implicit gradient regularization flow, where you see that there's an additional kind of Hessian-related term in the gradient flow there. And if you actually include all the terms of order eta, of any order of eta, and ignoring, say, the high order gradients of your objective function, then you can actually construct the so-called principal flow, which is defined by these power theories here that is kind of related to the Hessian and the gradient. So this principal flow actually admits a very simple, very concise form, which looks like this. Here, U and the lambda here corresponds to the eigenvectors and eigenvalues of your Hessian matrix. Okay? And your flow is defined by this sort of logarithmic function and with some matrix multiplication here with eigenvectors. Okay. So what's nice with this principal flow that the authors shown that it will actually be able to model sort of the oscillation behaviors of gradient descent, which is not captured by these other flows. Let me just give you this simple quadratic example, right? If we're talking about this quadratic function, and if you apply, say, gradient descent with a constant step size, and let's say if you're going to use a very large step size, then gradient descent will actually overshoot, right? It will jump from this point to here, this point here, whereas it will basically miss this local minimum here. But if you apply, say, for example, but if you compute gradient flow and this implicit gradient regularization flow, you'll see that they will actually be attracted to the local minimum and will not really capture this escaping behavior here. So the principal flow actually manages to, lift the dynamics to the complex space and being able to capture this overshooting phenomenon. And more interesting, it has been shown that for quadratic objectives, this principal flow can exactly recover the iterates of gradient descent. By exactly recovering, we mean that at the discrete time points, if you look at the k times eta, eta is the step size, k is the number of iterations, your gradient flow of x at eta k, k times eta is exactly going to be the case iterate of your gradient descent. So now let's move to the noise setting, right? In the noise setting, of course, one simple idea is just to add this addition diffusion term to capture the noise evolution. And here, the sigma corresponds to the covariance of the noise gradient. And it has been studied actually in many work, and particularly in this seminal work by Vienna and co-authors, that they've shown that this gradient, this SDE actually is proven to be like order 1 weak approximation for stochastic gradient descent. So following their name fashion, we're going to just call this stochastic modified equation 1, SME 1. If you add the same diffusion terms to the implicit gradient regularization flow, right, just the original flow there, and you add this diffusion term here, it has been proven that this is a second order approximation, weak approximation for stochastic gradient descent. And this is also known to be the best, order best approximation, as far as we know in the literature. And as a side note, I should say that there are also lots of recent works, I think, by Dela and also Radu on analyzing kind of the convergence rates of stochastic differential equations or these stochastic differential equations. But here in this talk, we're going to focus primarily on approximation, right? Not about convergence. So surprisingly, though, we've shown that even for very simple quadratic objectives, these existing stochastic differential equations fail to model the behavior of stochastic gradient descent. Here I'm going to give you two simple examples. The first one is some non-convex quadratic here. And suppose here in this case, the origin here, 0, 0 is indeed a saddle point. And let's say we're going to initialize our stochastic gradient descent somewhere nearby the saddle point. Right? If we're going to use a constant step size, we know that stochastic gradient descent will immediately drift away. Right? That is reflected by this black curve here. But if you look at what is the dynamics of, say, for example, SME2, you see that it will actually, again, stabilize around this saddle point, and it will actually converge to the saddle point. And here is another example where we have, say, another convex quadratic function. If we're going to start again at the origin, which is the local mean in this case, and if we're going to still use stochastic gradient descent with constant step size, we know that it will again drift away, right? Escape from this local mean, and this is reflected by this sort of this curve here, black curve, where the y-axis is the expected value of your function, objective function, right? So it will drift away from the local mean. But if you look at both SME1 and SME2, they will all get tracked or get stuck in this local minimum, and will actually converge to that local minimum. Yes? That's a very sharp observation. This is something also we try to understand. I think the explanation here we think is because SME1 is a very bad approximation, so there is just too much error there. That's why that large error or bias leads to this, right? This phenomenon, we see that it actually is not really attractive to the saddle point there. In that case, in this example, because it's a really bad approximation, so it does not really reflect what's going on. Yes. Yes. Mm-hmm. Mm-hmm. That's a good question here. Okay, sorry. So in the plot I shown here is the average behavior. Right. So here I plotted. It's good. Okay. So here basically I plotted like I run 1,000 times, right? 1,000 different rounds, and this is what I plot the average outputs. So yeah. Yes. What's the noise distribution? Here is just state independent Gaussian distribution. Yeah. Other noise distribution. We only checked Gaussian. We didn't check other heavy tail or other noise distribution. Any other questions? Okay. Cool. All right. So you might think then, what about if we use principal flow, right? I just introduced you. Actually, the principal flow gives you, seems like a better approximation, at least in the deterministic setting, right? So here's what we, the naive sort of stochastic principal flow, what we call, right? We just added this diffusion term to it. And turns out, again, it actually does not really fully capture the escaping behavior. Here's just one example where you have piecewise quadratic function where you have two local minima here, right? There is a bad local minima here, right, at 0. There's another good local minima here, right, at x equal to 5. Okay? If you run stochastic gradient, let's say we're going to initialize from this local mean here, and if you run stochastic gradient descent with constant step size, it will actually, right, escape from here and gradually convert nearby to this global mean. Okay, this is what you shown on the right. You see this black curve is the behavioral stochastic gradient descent, right? Y-axis is basically the expected value of the eta rays, right? You see it gradually converge to somewhere nearby the local minima here, or the global minima here, right, with some gap because we're using constant step size, which is roughly of size 1, 0.99. That is the step size we use here. But if you look at the stochastic principal flow, it will actually again stabilize around this local mean here. So it does not really capture this escaping behavior of stochastic gradient descent. So what is missing in the picture, right? What's really went wrong with all these existing stochastic differential equations? Any ideas? I guess smart people probably already have an answer to that, right? It's because we're not really including the Hessian information in the diffusion term, right? We needed to also try to incorporate this Hessian information there, not just in the drift term, but also in the diffusion term, right? That's exactly where our contribution is. I'm not sure if I will have enough time, but let me just first give you a preview of our results, and then we'll see if we have time to go into the details. Okay, so here's basically our proposed stochastic differential equation, which is called the Hessian-Aware SME, and I have already spoiled to you what are the behaviors, as you can see in the previous. These green curves is basically the performance of our SDE. Similarly here, these are the green curves. This is how HA-SME performs, and it actually matches very closely with how SGD behaves. All right. So the message here is that we consider both Hessian information in both the drift term and also the diffusion term. And the drift term here, we just follow the same as the principal flow. And in the diffusion term, we're going to define it. We actually derive it as the following convergent power theories, which have a very simple, concise form with the square root of some matrix. Right? This matrix S is defined by some entry-wise, multiplication between this matrix and some other matrix, which is defined by the eigenvalues of your Hessian. the Hessian is going to be the true objective F, yes. Right? Right, yes. So in terms of this is actually the whole most heavy lifting part is really how to, simplify all this to get this concise form. And, it takes us nearly 20 pages to achieve this. But here is basically the nice looking form here. As you can see that the first question you might be wondering, right? So this is square root of some matrix. Then of course it's only well defined if this matrix S is positive semi-definite. Right, and this does not always hold true if you use arbitrary, say, step size lambda, eta there. So we've shown that, in fact, this SME is very well defined if F is a continuous third order continuous and your covariance is positive definite, and these following two conditions about your step size is satisfied, then this is actually a well-defined SDE, and also it admits a unique strong solution. Okay, so here are the two kind of sufficient conditions. The first condition says that eta, has to be small, less than 1 over basically the largest eigenvalue of your Hessian, basically the smoothness, 1 over smoothness, and also that we assume that the covariance and your Hessian actually commute. Okay? And this might sound like a strong assumption, but in fact, many recent work, I think somehow my reference is so now I have the reference. So it has been actually empirically verified and also theoretically verified that for many problems, actually the covariance near the local minimum or global minimum is indeed behaves similarly as the Hessian. Okay? And this basically says that the eigenvectors of these two matrices has to be aligned. Okay? If they are not aligned, if they're not commutable, then we just need to set eta to be relatively small. Not as small as 1 over, web has to be much smaller than 1 over L, but this is still just some constant. Okay? If either of these two conditions hold true, then the SD is indeed well defined. So how does it approximate stochastic gradient descent? We also shown that this is indeed and also an order 2 weak approximation for stochastic gradient descent. But we did some, even because this doesn't really differentiate it from SME2, so we did some more fine-grained analysis and shown that actually it gives you much better dependence in terms of smoothness if you look at the weak approximation error. So here, if I define lambda as the maximum, the smoothness, the maximum eigenvalue of your Hessian, then you can show that with SME2, it actually scales quadratically with lambda. Okay? And with stochastic principle flow, we've shown that it scales linearly with lambda. For our SDE, it does not have any dependence on lambda. Right? This makes a sharp difference between these approximation bounds. Especially, it is important in the case where eta is relatively large. Say, for example, if eta is in the critical region, which is roughly of order 1 over lambda, then this makes a huge difference between these different approximation bounds. And this sort of explains why many of these existing SDEs does not really capture the escaping behaviors because they do not really approximate SGD well enough. And also more interestingly, we've shown that if we're looking at quadratic objectives, then this SDE actually will exactly recover the iterates of SGD. Okay? And particularly, we're looking at quadratic objectives where we have state-independent Gaussian noise. And by exact recovery, we mean that the distribution of the SDE at 8 times k has the same distribution as the iterate xk of stochastic gradient descent under similar sufficient conditions we say before, as long as the SDE is well defined. And you might think this is not really too surprising, given that it's a quadratic function, right? Any linear, you could probably come up some linear SDEs that approximate well. But we've shown that indeed this is not that easy. We've shown that if this covariance sigma and your Hessian do not commute, and if your sigma is not positive definite, then actually you cannot possibly construct any linear SDE that recovers SGD exactly, no matter how small you choose the step size. Right? The high-level idea here is that if, for example, your matrix A in your Hessian or your matrix A here is 4 rank, But if your covariance is rank deficient, then you can imagine that if you run stochastic gradient descent, right, the covariance of every iterate will still be rank deficient. But if you say consider stochastic differential equation, right, in continuous time setting, right, your noise will be introduced at infinitesimal time intervals, right, and this will be subject to just transformations of your drift term. And if the eigenvectors of your drift term A and your covariance do not align with each other, then this would immediately lead to some full rank covariance for your SDE. That's why you cannot possibly recover it if this does not hold. You have 3 minutes? 2 minutes. Okay. So let's see what you would like to see. I can I can tell you a bit about how we constructed this, how we come up with this SDE, or we can also look a bit into sort of the more detailed approximation guarantees. All right, maybe I'll show you how we constructed this SDE. Right, so the idea is basically we're going to extend this backward error analysis to the stochastic setting by introducing these diffusion terms, which is represented by these power theories here, and we're going to identify what is exactly these G's and H functions by matching, right, your SDE and SGD, right, and particularly we can do a semi-group expansion of your SGD, and you get all these Taylor expansions, right? We can also do a semi-group expansion on your SDEs, and you get these Taylor expansions. And now we're going to match basically, all these order eta p, right, by setting basically these phi functions and the psi functions to be the same. Okay, and we then try to do it by matching these. We try to derive what is exactly p and h. Okay? So this can be solved iteratively. You start with p equal to 0, right? You can easily figure out what is z0 and h0. This exactly leads to gradient flow. If you set p equal to 1, right, you can easily calculate what is z1 and h1. This gives you basically the implicit regularization flow with the same diffusion term as we discussed, SME2, right? However, if you start to look at what happens with p greater than equal to 2, suddenly you will see that you will get into a overdetermined system because there are only 2 free variables, HP and GP, you want to figure out, but there are p plus 1 terms. Because there are p plus 1 terms related to, you wanted to match all the, from first order, second order to p plus 1 order of your test function. Hence, this becomes overdetermined. You cannot really figure out what they are. So basically, in the end, we basically adopt these term selection rules by ignoring all the high order gradients of your Hessian, of your function f, high order gradients of your test function, high order gradients of your covariance. And then this will lead to a well-defined system, and you can actually uniquely calculate what is G and what is H. And that gives us this particular SDE. And I think that gives you kind of a touch of how we derive it. Yeah.